In this video, I introduce maximum entropy deep inverse reinforcement learning. We have introduced the maximum entropy deep inverse reinforcement learning. Now we just briefly go over the key points in the method. First, if a real-world function is not linear, so we need to use the deep neural network to approximate the nonlinear real-world function. I mean, so we use the deep neural network to describe the relationship between the states and the real-world functions. Because the real-world function in reinforcement learning is related to the policy, so we need to combine this real-world function with the policy together to train this neural network using the expert demonstrations. Second, we use the cumulative real-world over the trajectory sigma to define this probability distribution P over the trajectory sigma. We use this exponential to express this P, make sure this P is a positive. And then based on this P, we define entropy loss function. It's a loss, this is log P. And then we separate this entropy loss function into two terms. First term is related to the trajectory D, and second term is regularization. To use a gradient descent to update the parameter theta, so we need to calculate the gradient of the loss function, and in two terms. And the fourth term is in this difference times the gradient of real world with respect to the model parameter theta. Second term is regularization. And use the definition of the feature count is equal to P, the sum of the P over all the possible trajectories. And this mu D is the feature count under the export policy. And then now we can use the dynamic programming to calculate the difference between this feature difference under the export policy and this feature difference under the learned policy. Here is the method description. First, we randomly pick up a theta distribution, and then we select states from the export demonstration as an input to the neural network to find the real-world function R. From this R, we can use it in the dynamic programming to estimate the policy at the state S and estimate the feature count and the learned policy. The first step is the policy improvement. That means we from all the possible terminal states in a backward path to calculate the expected Q at the state S and the selected action A. And then we also calculate the expected state value function at the state. And then now we update Q and V from all the possible state, initial state, and all the possible trajectories. Once we get the convergence Q and V, then now we can use this exponential formulation to calculate this policy pi. This policy pi means the probability of action A at the state S. And then we use this policy pi in the policy evaluation step. That means we need that this pi at the state S propagate along all the possible trajectories until the terminal state, see how the possibility distribution over all the possible trajectories or all the possible states. The purpose is to see at a different state on the trajectory, how can we take action and what's the probability. And then we get this calculated the feature counts, compare with the feature counts and the export policy. See if they are close to each other or not. If they are close, that means the learned policy is close to the export policy. And then if we only calculate this gradient, we don't need to use this expectation, because it's just like a stochastic gradient descent method. We can randomly pick up one state is okay. However, now we need to use this difference to judge, we need to terminate the model training or not, because we use this difference as a criteria. And once we get this gradient, then now we can use this gradient to update the model parameters theta. Once we get this theta, then you give me a new trajectory. I can use this neural network to estimate the reward function, and then I use the reward function in the reinforcement learning to find the optimal policy for agent. And here, let's see the briefly idea what about the maximum entropy deep inverse reinforcement learning method. Here we pick a trajectory, this states distribution along the trajectory, and then we map these states to the feature vectors that are used as the input to the deep neural network. And then we estimate this reward function. And then we use this reward function in the dynamic programming to estimate the policy pi. And then from this pi, we propagate to all the possible state and trajectory to estimate this feature count and the learned policy. And then we compare with the feature count and the export policy. And they use this difference combined with this gradient of the reward function with respect to the multi-parameter theta together through the backpropagation to train the neural network. Once we get this network is convergence, then this feature count is close to the feature count and the export policy. That means we found that we learned the policy is close to the export policy. And then if you give us a new trajectory, we can use the neural network generator, the reward function, and then use this reward function in the reinforcement learning to find the optimal policy for agent. For more details, please check with this reference. Thanks. Bye.